Hey everyone, and welcome to this explainer. Today, we're going to trace an absolutely epic 35,000-year human journey of problem solving. We're talking about the mathematical foundation of our modern world. We're going to unpack a super fascinating chapter of history to see how the number system we use literally every single day didn't just drop out of the sky. It evolved, and the story of how it happened is incredible.
So let's just dive right in, shall we? Step back in time with me for a second. Long before humanity built cities or even thought about studying the stars, we had a really fundamental practical problem. We needed to keep count. Imagine you're living thousands of years ago in a small agricultural settlement right along the banks of the Saraswati River. You've got a herd of cattle. Every morning they head out into the dense forest to graze, and every evening they come back. But how do you actually know for sure that a calf hasn't wandered off? You don't have words for numbers yet. You definitely don't have written symbols. So what do?
Well, you'd use a really clever survival-driven trick called one-to-one correspondence. It's actually pretty simple. For every cow that left the settlement, you, the herder, might just drop one pebble into a clay pot. Then in the evening, for every cow that came back, you take one pebble out. If the pot was totally empty at the end of the day, awesome, your herd was safe. If you still had pebbles left over, well, you've got missing cows. This brilliantly simple act of just matching one physical object to another was the absolute birth of what we call natural numbers. This simple counting numbers of 1, 2, 3, and so on.
Okay, so here's our visual roadmap for how we're going to build the blocks of our number system today. We'll start with the dawn of counting, look at some history literally written in bone, explore the massive revolution of zero, fill in the gaps with fractions, tackle the wild discovery of irrational numbers, and finally, unite it all on the real number line.
All right, part 1. The dawn of counting, or, as I like to think of it, mathematics right there in the dirt.
Moving right along to part 2, a history written in bone. Let's meet the first mathematicians.
Our story starts way before classrooms and whiteboards. Like we just saw with our cattle herder, mathematics was purely a practical survival tool. It started in the dirt, on the bark of trees, and, as it turns out, carved into the remains of animals. Now, while the decimal place value system we use today was ultimately perfected over in the Indian subcontinent, the absolute earliest physical evidence of humanity recording natural numbers takes us deep into the heart of Africa. The very first mathematicians didn't use paper. They used tally marks carved deep into bone. This is the Ishango bone. It was found near the headwaters of the Nile River in the Democratic Republic of Congo, and it dates all the way back to around 20,000 BCE. It's got these 3 columns of asymmetrical notches. But get this, it's not just random scratching. This is a literal mathematical marvel. One of the columns deliberately groups the notches into 11, 13, 17, and 19. If you know your math, those are the prime numbers between 10 and 20. Another column even shows off the concept of multiplication by doubling. It is just mind-blowing proof that the abstract concept of a number is tens of thousands of years old.
Let's look at the timeline to see how this whole thing scales up across civilizations. We can bridge the gap from the 35,000-year-old Lubombo bone and the Ishango bone in Africa all the way over to ancient India. Because as civilizations grew, like in the massive Indus Valley, merchants suddenly needed to trade standardized weights of spices and copper, and to do that, they needed bigger numbers. By the 4th century BCE, Vedic philosophers were naming massive, mind-boggling numbers up to 10 to the power of 53. Just think about the huge conceptual leap it takes to explicitly use powers of 10 at that kind of scale. It completely set the stage for the place value system we use today, and honestly, it paved the way for probably the single most important mathematical invention in human history.
Which brings us nicely to part 3, the revolution of zero. This is when nothing literally became something.
For millennia, the number line basically just started at 1. Think about it. If you had 5 apples and gave all 5 away, you didn't really have a number to represent your current state. You just had a void, a lack of apples. Sure, earlier civilizations like the Babylonians used placeholders in their math, but a massive, monumental breakthrough happened when nothing was actually transformed into a real, operable number. And this breakthrough is deeply rooted in Indian philosophy. In vast Buddhist literature and the Upanishads, there's this powerful concept of shunyata. It's a profound state of emptiness and tranquility, basically the ultimate goal of yoga and meditation. Because Indian thinkers already revered this meditative state of emptiness, they had the perfect philosophical framework ready to welcome nothingness. It wasn't some scary void to them. It was a completely valid, essential concept. So, this philosophical emptiness eventually crystallized into the mathematical zero, or shunya.
So when did this deep philosophy turn into hard, functional math? Well, in 628 CE, an Indian mathematician named Brahmagupta officially transformed this void into a fully operational number. he explicitly defined 0 as the result of subtracting a number from itself. He actually laid down the fundamental laws of arithmetic for 0 that we literally still use today, like how adding or subtracting 0 leaves a number totally unchanged. And brilliantly, he didn't stop there. He also formalized negative numbers, essentially categorizing them in a really practical way as debts as opposed to positive number fortunes. Boom! Suddenly our number line is stretching backwards right past 0.
Part 4. Fractions and rational numbers. Time to start filling in the gaps.
All right, so with 0 and negative integers firmly on the board, the number line was growing fast. But humanity still needed a way to account for parts of a whole. You know, like half a bag of grain or a third of a copper ingot. This everyday necessity led straight to the creation of rational numbers, completely filling in the spaces between our whole integers. A rational number is really just any number that can be expressed as a ratio or a fraction of two integers, what mathematicians call P over Q. The absolute only rule here is that the denominator, Q, cannot be 0. This neat little system covers all our fractions, but it also covers our integers too, because honestly, a number like 5 can just be written as 5 over 1.
And this beautifully illustrates one of the almost magical properties of rational numbers, their density. Think about it like this. Between the numbers 1 and 2, there is exactly 1.5. Between 1 and 1.5, there's 1.25. No matter how insanely close two fractions get on the number line, you can always squeeze another one right in between them just by calculating their average. Because of this infinite density, it totally feels like rational numbers must completely fill up the number line, right? Leaving absolutely no gaps whatsoever.
Well, actually, scratch that. Part 5. The irrational discoveries and the unfillable gaps.
Because do rational numbers really fill the entire line? Despite that infinite density of fractions we just talked about, mathematicians eventually hit a massive brick wall. The ancient Greeks stumbled onto a logical disaster that totally shook their understanding of the universe. Our seemingly perfect number line still had gaps in it. And this crisis came from a shockingly simple geometric shape. If you draw a perfect square where every single side is exactly 1 unit long, the Pythagorean theorem tells us that the diagonal measurement cutting across that square is the square root of 2. But when mathematicians actually tried to write the square root of 2 as a fraction, as a ratio of two integers, they found out that it famously, impossibly, cannot be done. It is what we call an irrational number. Around 400 BCE, there was this mathematician named Hippasus who completely shocked the Pythagorean school by proving this mathematically. He used a super brilliant method called proof by contradiction. He basically started by assuming the absolute opposite. He said, okay, let's just pretend the square root of 2 is a simple fraction. And then he systematically showed how that one assumption entirely breaks the fundamental rules of math, leading to a complete logical disaster. This proved beyond a shadow of a doubt that irrational numbers are real, and that our beautifully dense web of fractions actually had infinite unfillable holes right in the middle of it.
All right, we're in the home stretch. Part 6, Uniting the Real Numbers, the grand finale.
To complete our 35,000-year evolutionary journey here, we have to find a way to weave these two totally different, conflicting types of numbers together into one cohesive system. The easiest way to tell them apart, to see their kind of mathematical fingerprint, is just by looking at their decimal expansions. If you divide a rational fraction, it's always going to do one of two things. It either terminates cleanly, like 0.135, or it falls into a perfectly repeating loop, like 0.3333 going on forever. But irrational numbers, things like the square root of 2 or pi, they just produce chaotic, non-repeating decimals that continue infinitely without ever settling into a clean pattern. So what exactly happens when we finally bring them together? Well, when we beautifully unite the perfectly patterned, dense web of rational numbers with the infinite, chaotic gaps of the irrational numbers, we build this, the real number line. It's a single, continuous, unbroken spectrum. From the counting pebbles of an ancient cattle herder to the negative debts of ancient Indian mathematicians, all the way to the infinite chaos of pi. Every single length, every temperature, literally every physical measurement in the known universe has a permanent, unmoving home on this continuous line. We've essentially built the universe's ruler. But here is a really provocative thought to leave you with today. To solve the deepest mysteries of quantum mechanics, and honestly, even just to engineer the mobile phone you might be holding right now, mathematicians eventually realized that the real number line wasn't enough. They literally had to step completely off the line into a brand new dimension, inventing something called imaginary numbers. But how does that even work? No way, right? Well, that is a perfectly fascinating explainer for another day. Thanks so much for joining me on this incredible journey through the world of numbers. Keep learning, and I'll catch you next time.